and we are going to go to this. Okay, so all right. First thing first, I have shown you, but let me write it down again. Let's try in 3D. So let's say this is your roof, okay? And the beams coming in, and then we have the column here. So I draw this grid line because it looks more simple and it's easier to draw. So let's say if this is the roof level, okay, the load on the roof right here, let's say if assume that this is your tributary area, okay? So this tributary area will be supported by this column, okay? And then this is a roof. And then this column will come down maybe at some distance. Okay, and then there you go, it's your second floor. Okay, and your second floor will have the beams, the stuff coming in again. And then this is your second floor. And with a slightly different tributary area, maybe, whatever. So let me change the color. Okay. And let's say this is your second floor. And that is its own tributary area of some kind. And you see very clearly from this picture that the load on the roof goes into this column. See, the load on the roof is black, and the black portion of the column will take care of the load from the roof. And then when we are at the second floor and we continue to move downward, that will be the portion of the column underneath the second floor. Okay, and this one will carry the load both from the roof and then from the second floor. So I can add that this one, you know what, this is confusing. So let me erase this first. And I try to write this as second floor. And let's say erase this first. Okay. And okay, this column will support the roof. Okay. And when you come down underneath the second floor, this one will have to support the roof and the second floor. Okay, so that means if I am going to draw the column load diagram, I will have something like this, right? And therefore you see the load from the roof. Okay, and then I change the color. It goes my second floor. And I will have the load on the second floor. Okay. So that this portion supports only the roof. And then this portion will support the roof and the second floor. And then, you know, you're gonna have the first floor on the ground. And now I used to mention this to you. It depends on whether or not you want to put the ground floor onto your structure. And then we have the abutment. Okay, the abutment. So the abutment may take the same load as this blue column, or it may take more load if you plan to put the first floor on beam. Okay, and in some part, let's say if we would have to design the abutment. Okay, so it depends on whether or not we set this, and we'll talk about this later when we reach that part. Okay, I haven't checked the details yet, but this is your column diagram. At least you should be able to draw this, and once you can see the load very clearly, your next step of the column design, you will have the right load. Okay, so is there any question? Hello? Is there any question on the column diagram? If you cannot finish your column diagram today, it's fine, because I told you about the column load diagram, but I never, you know, demonstrate this to you. But in the next step, in design phase number 2, where you need to design the column, you need to show this diagram. Okay. So there isn't any question. So brace yourself for the truss. Okay. Now it seems to be some kind of confusion with the truss a little bit. When you see the floor plan, you know, let's say I'm going to draw the plan. You have the grid line G, and then that's a grid H where somewhere, and then this is H prime that I just rename. Okay. Well, you see, in the drawing, it says it's like every 5 meters you have a column. Okay, but we say we use our imagination and give you the situation where you need to design the 6-meter canopy. So let's say one block is 1 meter. So this one is going to be longer than the span here. Okay, so keep in mind that this is your imaginary truss. Okay, this is your imaginary truss. Since Ajahn Sutthat and I wanted to be a little bit long so that it is more interesting. Okay, so you see, basically, all this part of the load will go on to the truss, because the truss becomes a main beam here, or the main girder, and all the load that the roof has, you know, will go on. Let's say this becomes a tributary area for each truss. All right, and then this becomes a tributary area. And all this load, if you want to include, will go on directly onto this column. Okay. And I say we use the 1.2 spacing. So that's a 6, so that's a 1. Let's say that's 1.2, 2.4, 3.6, 4.8, and then 5. So if you look at the plan, you should see these are the purlins. Okay, placing on the truss, you know, throughout the length, like that. Okay, so these are the purlins, that too, and should be around that too. That is a purlin at 1.2 meter. So to sum the load acting on the node of the truss, you would just need to look at the tributary width of the purlin, right? And if the spacing is 1.2, the tributary width here is also 1.2. Okay, so that's how you should get the load on your truss. Does anyone want to take a picture of this one? Or I can just write around here. And your truss, let's say this is your truss. And you're going to have the purlin coming in here. And the load here will be the reaction of the purlin from the left and then from the right. So it's basically, this load is the tributary width 1.2, right? multiplied by the load. And because you have a purlin from the left, half of the reaction is WL over 2, right? So that's a 2.5. And then you have another purlin from the other side, so it's multiplied by 5. Okay, that's how you got the load on the truss. Once you have the load on the truss, let's say, can I move on to the next page? I think I can, right? Okay. So now, let's say we are going to have the truss. I will try to draw it to my best ability, you know. Say this is a 3D. Say that's a R shape. Let's get the diagonal web or the vertical web, if you have any, out of the way first, because it's the most simple one. You see, if you look at one of these webs, you see that the unbraced length is basically the length of the member, right? So that becomes the unbraced length. And because it is connected to the top and the bottom chord, so you may assume that K is equal to 1 very easily. But that should not leave any question, all right? So now, let's say I am going to talk about the typical truss. Remember that your typical truss, let's say typical truss, is a simple beam, and positive moment. When you have a positive moment, it means that top is compression and bottom becomes tension, right? When not typical, let's say our case of the canopy, because it's a cantilever, or sometimes it's part of the continuous beam, where you have the negative moment. This time your top chord will become tension and your bottom chord will become compression. Oops. Okay, so tension is nothing, because let's say when you design tension, it's just yielding and rupture. So let me summarize it here. That tension is a piece of cake. So that's taken care of. Now it's time for compression. Now when you look at the truss, listen very carefully. Even though when you perform the analysis, you would look at this member and then this member, that member, that member, and use either the method of joint or method of section. But you always look at this one as one member in your analysis. But in the real world, you know, we always construct the truss so that generally this is one long member. Okay? Generally this becomes one long member. Okay? And you guys ready? When you look at the top chord, because of the length, you know, it's throughout the member. It has two buckling axes. Okay? I will draw this again, but side view. When I look at the side view of the truss, like this. When, let's say, our top chord is under compression, if, let's say, I have a member maybe it's a tube, it's a pipe, it's okay. If the buckling is going about this axis, you know, it rotates about this axis, it means that your member is going to dance up and down, correct? That means because of the presence of the joint, your member can only dance up and down with the joint becomes the brace point. Okay, so let me try to write as much as possible, up and down. So the, say, joint becomes a brace point. Okay, so you know it rotates about this axis. The horizontal one, you may call this one X. So when the rotation moves and about this axis, your member dances up and down. Okay. Is there any question? Now, let's see the truss from the top view. I should write that this is side view. So side view, you will see the movement up and down, okay? That the buckling is the rotation about this, say, x-axis. Okay, now let's move on. If I look at this truss, again, the same truss, but this time I see it from top view. What am I going to see? I will see just the line, right? I can no longer see the diagonal members or the vertical webs if I have any. So let me try to thicken it. From the top view, I can only see this. Are you guys with me?
Yes.
Okay, so if I use the same picture of the cross section here, the buckling will now occur with the vertical axis. Okay, so when the buckling occurs with the vertical axis, or maybe I try to do it 3D, let's say if it helps you. Let's say if you look at this member, the axis for the buckling of the side view is this axis, correct? When it rotates like this, your member will dance up and down. But when you look at the top view, when the buckling is going to occur, it's, you know, your member is going to rotate about this axis. So that means your buckling will come out of the plane of the truss, and your webs can no longer help you because the web is in this plane and you cannot see them anymore. So your truss can move, say, left and right. Out of plane. Okay, so what would be the brace point then? You no longer have the, if you look at this picture, your webs can help prevent the up and down movement, right? Webs help prevent up and down movement or displacement. That's more like it. But it doesn't help restrain this blue member to move in and out, left and right. In this direction, there is no help. The only help in restraining the movement of the truss, when you look at the top view, you see that it goes, like this, will only come from your purlins. Okay? If you have purlins, let's say, if you have purlins coming in like this, purlins, oops, here we go, what's going on? Okay, it's back pretty easily. Good for us. If you have purlins, what you should have, the purlins that sit on the top chord can help prevent the movement of the truss, in and out of its own plane, because you need to connect the purlins to the truss. So let's say if I have the purlin at every other panel, the triangle can be called a panel. Let's say if I have another purlin here, you will see that this truss will be free to move out of plane from this point to that point. Okay, so let's say if I come down here and I say I have the purlin here and here, when your top chord is going to buckle, it will buckle from one panel to another like this. But when you look at the top view, you can now see the purlin here and then the purlin there. So the buckling will be exactly this blue line. And this becomes your unbraced length. So when you look at the side view, the up and down movement, this is your unbraced length. Now, because this is how much your member can move, right? It has a brace points from the webs. But when you look from top view, these webs cannot help, and what you have as a help comes from the purlins. And for the top view, this becomes your unbraced length. And for this, the first case, when you look at the side view, you may say, in this case, K is equal to 1, because it still resembles a simple beam somewhat. But for the second case here, because the member is solid entirely, and we are talking about the entire member coming out. So in this case, even though the unbraced length may be longer, you may take K as 0.65. Okay. I have the same picture here in the slide of chapter 3. Okay. But you guys have done the truss with Janjulapot, right? In your statics. So it's the same here. That, if we look at this gray plane, all right, can I erase this first? Okay. It's a similar situation where I just drew on the note. But in this case, if you look at this gray plane, you will see the picture of the truss, just like what I drew, and you will see that this member will buckle. Too bad I don't have the orange color. It's like that. This orange color in here is basically this line. Okay, and this is the picture when we look at this plane. But from this, we look at the top view, and you see that the lateral bracing is something that you need to provide. And this is the truss. Okay, and therefore this deformation is what you can see from the top view, and therefore your truss is going to buckle like that. Okay, the same picture. And I also have the case to show you here that for the buckling of the out of plane of the truss. So let's see if this black line is our truss. Sometimes if you don't have the purlin, you see that in the roof in the factory, sometimes they need to provide extra truss just to brace the top and bottom chord of this truss. Okay. Is there any question? Again, there's another picture to try to help you out. That when we look at this this truss in the plan supports this truss coming in from okay, here we go again. Let's do that. It's fine. This truss coming in from this direction. So when you look at the green truss now, it has only the red truss coming in. The green truss does not support any purlin. So if you look at the picture of the green truss, okay, this is the green truss that you see from the previous plan. When you look at the buckling of the top chord in this, the buckling about this horizontal axis, you see the member can move up and down between the joint. But when you look at the buckling about the vertical axis, you need to look at the top view. You see that the top or bottom chord will buckle in according to the braces that you have. Okay, and it's going to be very much fun for your project, because when you consider the canopy that you have, whatever your configuration may be, you will have, let's say, your purlin will sit here, right? But because it's a canopy, so it's a cantilever, so this is tension. Compression is down here. And yeah, you don't have anything to brace that one in the out of plane direction. Okay, but the good thing is that I think for aesthetic point of view, we are going to use the pipe which has only one R pipe, just, you know, only one R. So you just figure out the maximum unbraced length and you're fine. You don't have to check both axes. So that's the beauty of the pipe. Okay, so those are the two things I want to talk about. So let's hear the question first. I want us to have a break before I start talking about the angle. Question, please. You know, this again is the real thing. This is the least that Ajahn Sutat and I have talked about this for quite some time, that let's say at least after taking the steel design class, you guys should be able to design the truss in the real world. Because it is very likely that if you are going to deal with the steel structure sometime in the future, it is going to be the truss. So that is why we want you to have a real project about the truss. So at least, you know, you go out and then someday someone brings the drawing of the factory to you. Hey, can you design a factory? You would say, yeah, sure. And most likely the factories will have the truss roof because the factory wants a large area underneath. So you can't have columns like every 4 meters, you know. So the only choice they have for the roof would be the truss. And you see, this is no more than what you have done with statics. The analysis of the truss is the same. The additional knowledge that you should have here is the treatment of the unbraced length. Okay. So is there any question? Hello? So let me stop the share and let me try my best to use what I found in my other room, see if I could demonstrate the behavior of the truss for you. It's going to be difficult, but let me try. Okay. So here we are. I found this tea, you know, that's pretty dirty. So it took me like a few minutes to clean it up. Let's say if this is our either top or bottom cord that will buckle under compression. Okay. So if I say this is your side view and I may have the support coming in here like this. Okay. Let's say I have the support like this and I am all alone in the house. So let me try to find the best way to hold this up. Okay. Let's say this is my panel. Okay. You guys can see it. If the buckling is going to occur up and down, this top cord can buckle between the two nodes, right? Okay, it can buckle between the blue member and the black member. So this becomes unbraced length. But you see the axis of the top cord, so just too much for me to bend it in one hand. Okay, you can see that. If it's going to buckle in this direction, you know, the black one and the blue one I have here becomes the support. So you see the rotation here occurs with the horizontal axis, right? And the unbraced length becomes the length between the two supports here. But let me switch the member because I cannot bend it out of the plane in this axis. It's too tough. So let me put it this way. If this member is going to buckle out of plane, you cannot see it from this view, so I need to turn it upside down so you see something like this. Okay, so when I turn it like this, you see that by turning this stuff into this direction, you see the webs, the black member and the blue member doesn't help at all if the buckling is going to occur in this direction. Okay, so it can buckle freely, you know, if the web is in this plane. Okay, if I can just hold one web like this, you see, now when we look from top view, you don't see the webs anymore. And when the buckling occurs from top view, you see the member move out of its own plane. There is no help from your diagonal or vertical webs. That is why when you consider this, the only help you may get for your cord will be the braces from the purlins or from the extra truss you put in the system. Okay? Does that help? Better than not trying, right? All right, is there any question? Hello? I think I'm still recording it because I believe that some may find this new thing pretty hard to get into or hard to visualize. That's why I believe that whatever the questions you guys have will be extremely useful for everyone. That's why I'm still recording. So if there isn't any question, let's call this session over and we're gonna have a break, okay? So I will not entertain any question after I stop the record. Let's have a 15-minute break and then come back again, okay? So is there any question? 1, 2, 3, no. Okay, so I'll stop the record.